All right, welcome back to the Nearly Carbon Neutral Geometric Topology Conference. This is my talk, my research talk, and it's on quotients of Coxeter groups. And all of this is joint work with Olga Varghese. We've uploaded a paper to the archive a couple of weeks ago, and there's still research. We're still doing research with some collaborators in that direction, and I will tell you about it now. Okay, so first, introduction, quick reminder, what is a Coxeter group? So let gamma denote a finite simplicial graph, so finite number of vertices, no double edges, no loops. And M an edge labeling, going to the natural numbers bigger than or equal to 3 and infinity. Then we define the Coxeter group W gamma via the following presentation. So our generators are the vertices, every generator has order 2. They commute if there's no edge, and their product has order of the edge label if there's an edge and the label of the edge is not infinity. And if the label is infinity, we just put no relation. And I've given an introductory talk about these groups in case you've never seen them and want to learn more about them. If not, just understanding this is what a Coxeter group is completely enough to follow the talk, but there will be a lot of black boxes that we're using during the talk because we just study these groups and we need to know a lot about them. Okay, and what question are we going to ask? Well, the question we're asking is, to what extent is a Coxeter group determined by its finite quotients? Right, and this is right at the heart of residual and profinite methods, which is why I'm talking about this today. Okay, so starting point of our investigation. Given a group G, we denote by this curly f of G the set of isomorphism classes of finite quotients. And now, since the starting question that I just mentioned was a bit vague, let's be very precise here. What question are we actually studying today? So suppose W gamma and W omega are Coxeter groups such that their finite quotients are the same. Does this imply W gamma is already isomorphic to W omega? And I hope that I can give at least a partial answer to this question today. And partial results in that direction that we know of are, of course, if W gamma is finite, this is true. What's more, if W gamma and W omega are crystallographic groups of dimension less than or equal to 4, this is also true. So in fact, in that case, you don't need W gamma and W omega to be Coxeter groups. If you just know you have two crystallographic groups with that dimension condition, this implies they are isomorphic. And this is also true for some triangle groups. So there's a list of triangle groups that are even absolutely profinitely rigid in the absolute sense. So in that case, you don't need this condition for both of them to be Coxeter groups. But in particular, this is true for Coxeter groups. But these are really not like super many cases. So yeah, not too much is known at the moment. And so our idea was, okay, what's the ideal case for this? In what case would you really expect this to be true? And this would, of course, the best case would be the group is infinite, because about finite groups we know enough. And we want all the finite quotients to know all the quotients they can know. So in a sense, well, what that means is that every proper quotient of the group is finite. And now, if you've heard this, then you will think, oh, I've heard this definition before, and this already existed. And this is the definition of just infinity, as you can tell by the title of the slide. A group G is called just infinite if G itself is infinite, and every proper quotient of G is finite. Okay, and this has been studied in the past, so this is not a new concept or anything, but I think for the study of profinite rigidity, this at least from my intuition of mathematics, this seems to be a very good starting point where you would really expect some results to hold. And examples of groups having this just infinite property is, okay, the group of integers, infinite simple groups, and for us, the most relevant example is probably the infinite dihedral group, because this is a Coxeter group and it's infinite, and it's coincidentally, well, not really, but it is an irreducible affine Coxeter group. And some non-examples are, for example, many even-type Coxeter groups. So an even-type Coxeter group is a Coxeter group where the edge labels are all even numbers or infinity. And then very often you can just project down and end up with an infinite Coxeter group. And in case you're interested in explicitly constructing some quotients of Coxeter groups, there are some methods that we describe in our paper as well, because we really cared about quotients of Coxeter groups at first, and we really thought about methods to obtain quotients that are, again, Coxeter groups. So chances are, if you're given some arbitrary Coxeter group, that there's a method for you to find a Coxeter group quotient, and most likely an infinite one. Okay, but so now this best case scenario, when does it happen? Well, we were able to determine exactly when it happens, and that is in the following case. So let W gamma denote a Coxeter group. Then W gamma is just infinite if and only if W gamma is an irreducible affine Coxeter group. So irreducible means the defining graph gamma has one connected component, and affine means it acts nicely on a Euclidean space. So yeah. And if you want to learn more about irreducible affine Coxeter groups, I mean, there's, again, the first talk that I gave. Okay, so as always in these quote-unquote short talks, I'm going to talk about the proof, but I'm only going to mention the steps and ideas used, but not actually give you a proof. But I think this can give you a rough idea of how the proof actually goes. So first direction, suppose we're given an irreducible affine Coxeter group. Then we know affine Coxeter groups have a semi-direct product structure. This argument will come up again and again today, by the way. And semi-direct products of this form, z to the n times some finite group, have been studied with respect to just infinity. So there's some condition that you have to check on the action of the finite group on the z to the n. And you can do this for irreducible affine Coxeter groups and then figure out that, okay, this works. Okay, so the other direction, what we will show is that if we're given a Coxeter group which happens to be not irreducible affine, then it's not just infinite. So first of all, okay, if I'm given any Coxeter group and the defining graph gamma is not connected, then I end up getting at least two factors, and at least one of them is infinite, and then I can easily construct a quotient which is infinite by just, modding out one of the factors which happens to be non-infinite. Okay, so we can assume that gamma is connected. And if gamma was virtually abelian and connected, then it would be irreducible affine. So W gamma is not virtually abelian. And what was shown is that in the literature that a non-virtually abelian Coxeter group is virtually indicable. Okay, what is this notion of being indicable? It means, well, virtually means there's a finite index subgroup which has z as a quotient. Okay, and at first this might seem unrelated or something, but, well, z is an infinite group, and at least we now find a finite index subgroup which has z as a quotient. So maybe if we can be very clever, we can find an infinite index normal subgroup. And this is what you do. So what you show is a non-virtually abelian, virtually indicable group is not just infinite, And how do you do this? Well, the idea is you take a normal subgroup N, which is finite index, and you find a projection onto Z, let's call this phi, and then you consider the core of the kernel of phi. So the core is just the intersection of all conjugates of this kernel, and this will again be a normal subgroup. And then you need to think about this index. It's not too hard to see that this has infinite index. Where you really need to work is to show that this is non-trivial. But if you think about this for some time, you need to consider subdirect products and certain properties of them. But then you can show that this is non-trivial, and then okay, so if you're given these arguments show I'm given a Coxeter group which is not irreducible affine, well, then I find an infinite index normal subgroup, hence the quotient is infinite, hence we're not just infinite. So just infinite Coxeter groups are exactly irreducible affine Coxeter groups. So if we want to start investigating the finite quotient case where, well, the question we started with, right? I have two Coxeter groups. They have the same set of finite quotients. Are the Coxeter groups isomorphic? The case where you would really expect this to be true is the irreducible affine Coxeter group case. And this is what we studied. But well, first, before stating the result, I want to remind you of the general context. And the general context is profinite rigidity. But this is like a very brief reminder. So suppose C is a class of groups and let G be an element of C. We say G is profinitely rigid among C if, well, given another group H in this class C, which has the same finite quotients as G, this H already has to be isomorphic to G. And if C happens to be the class of finitely generated residually finite groups, then we say G is profinitely rigid in the absolute sense. And I assume that you've already seen this, but yeah, this is essentially the question that I started the talk with. And a very important theorem for us to study this question is the following. So let's start with this side. Two groups G and H have the same set of finite quotients if and only if G hat is isomorphic to H hat, and these denotes the profinite completion. I assume that you're familiar with the profinite completion. If not, we don't really like use it too explicitly. We just have some arguments about this. So you can just take it for what it is if you want to follow the talk. You don't have to be scared. And okay, this theorem is only true for finitely generated residually finite groups, but Coxeter groups are finitely generated residually finite groups, as I told you in the first talk. Okay, so examples or more examples of this, well, you can see the introductory talk, and at the very end of this talk, I'm giving like some literature to learn more. And there are 3 papers which study this question that I'm mentioning, and there are more examples and also examples where G hat isomorphic to H hat does not imply that G is isomorphic to H. So feel free to look there and if you think this is interesting. Okay, but now let's get back to what we could prove. So let W gamma denote an irreducible affine Coxeter group. Then W gamma is profinitely rigid among the class of Coxeter groups. So if I'm given another Coxeter group W omega, some Coxeter group, it has the same finite quotients as W gamma, then it already has to be isomorphic to W gamma. Okay, and again, ideas of the proof idea. So we start with W gamma, semi-direct product, and now you need to know stuff about the profinite completion and how it works with semi-direct products. Namely, it works very well. So we can just do profinite completion on each factor, and our profinite completion is then again a semi-direct product. But one also has to do something with this action, right? So I'm not mentioning the action here, but well, obviously it's not the same because this is not the same group as that one. Okay, so now assume W omega is a Coxeter group, which has the same profinite completion as W gamma. Then, since W omega is finitely generated, residually finite, W omega embeds into its profinite completion, which is isomorphic to the semi-direct product, which is a virtually abelian group. So my W omega itself is virtually abelian. And now I know a lot about Coxeter groups. Virtually abelian Coxeter groups have a very, well, nice structure. Namely, they look like this. They look like a direct product. W omega 1 times W gamma 1 times dot 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 times W gamma n, and I haven't told you what the contributors are. W omega 1 is a finite Coxeter group, and each W gamma I is an irreducible affine Coxeter group. And this really uses a lot of the theory of Coxeter groups to end up with this. Okay, so we're moving closer to W omega being an irreducible affine Coxeter group. Well, first we want to see that it's in fact an affine Coxeter group. Well, I mean, that we want to see that the finite part is equal to 1. And how does one do this? Well, the idea is to look at the existence of non-trivial finite normal subgroups. And one can show that given such a semi-direct product, if this semi-direct product doesn't have non-trivial finite normal subgroups, then neither does this profinite completion. And since W gamma is irreducible affine, we know it doesn't have any non-trivial finite normal subgroups, because then the quotient would be infinite, and we know that W gamma is just infinite. So this can't happen. So W omega 1 has to be equal to 1. And now the next step, which is a bit harder, is to show that this n is actually equal to 1. So we in fact are given an irreducible affine Coxeter group here. And what's the idea? Well, first you look at the abelianization. Abelianizations work really well with profinite completions. So this allows you to reduce this number of factors quite a lot and reduce the number of cases you have to check. But there still remain some cases where the abelianization is not enough. And these cases you have to really look at, and then you have to also do some analysis on, okay, which finite Coxeter groups split into a direct product, and there's work to be done here. But if you're careful and think about this for a while after the reduction with the abelianization, you can really see that this n actually has to be equal to 1. And then, okay, we know W omega is a semi-direct product, z to the L, with a finite group E now. And then you use arguments from group theory, essentially, which is not too easy to do, by the way, but you can do this and show that, well, K is equal to L and F is isomorphic to E. So essentially we have the same semi-direct product, but we don't know that this action is the same. But this again works with irreducible affine Coxeter groups because they are determined by these diagrams. And okay, if you know that the finite group is the same and the z to the k is the same, then you know they are isomorphic. Okay, so this is nice. So it turns out that looking at the just infinite Coxeter groups was a good starting point, because at least we could show this result. But of course, the next question is now, what happens if we don't require the other group to be a Coxeter group? So, or in other words, the next research question is, are irreducible affine Coxeter groups profinitely rigid in the absolute sense? And I can't answer this question. The only thing I can give you is a very basic example. So what's potentially the smallest / easiest irreducible affine Coxeter group that we can think of? It's the infinite dihedral group. So if the answer is supposed to be yes here, then it certainly should be yes for the infinite dihedral group. And it is. So this is what we also showed, is that the infinite dihedral group D infinity is profinitely rigid in the absolute sense. And again, I want to give you some ideas of the proof. So suppose G is a finitely generated residually finite group, which has the same profinite completion. And then we do similar arguments again. So G is virtually abelian, because the group on the right-hand side is virtually abelian. And then, since we know that D infinity has a factor isomorphic to Z, but no factor isomorphic to Z to the 2 or any bigger exponent, we can conclude that K is equal to 1. Again, this is not super easy to do, but it's true. And then we know a lot about groups that are virtually Z. There's a lot of research done on those guys. And essentially, there are two cases for groups that are virtually Z. Either they look like a semi-direct product, where now this F, the finite group, is normal, or this group already projects onto D infinity with finite kernel. And now again, we can reuse arguments that we already used. In the first case, there's a finite normal subgroup, which D infinity doesn't have, but this thing has. So the profinite completion has also a finite normal subgroup, which is not trivial, of course. So this can't happen. And in the other case, there's a lot of literature. Well, there's this one paper, which I'm going to show you later. Well, I'm going to show you which reference this is. And you can see that this also gives you a contradiction. So, at least in this very basic case, this works. And let me finish by saying that I'm currently working on this question with Sam Corson, Sam Hughes, Olga Varghese, and, well, myself. And, well, we think that we can probably show that the irreducible affine Coxeter groups are actually profinitely rigid in the absolute sense, and we think that you probably need the irreducible case, the irreducible word here for this to be true. But this is ongoing research, so don't take this for granted. I hope that potentially in a couple of months I can tell you more about this. So if you found this interesting, then definitely look on the archive in a couple of months. There will hopefully appear a paper that can give you more information on this, on this question. Because the starting point, the foundations have been laid. It seems like this is a reasonable question to ask, and we now have some ideas on how to study it, because we studied the easier cases first, and these seem to be working very nicely. So, thank you for your attention, and thank you for the invitation to speak at this beautiful conference. And these are the additional things you can read. Of course, there's our paper, but these are also the things that we use. This is the um, no, this is the paper that I was referring to in the last proof, and the other ones are really for more examples and the stuff that I mentioned before. So if you have been paying attention, thank you again. Thank you for the opportunity to speak here, and I wish you all a beautiful conference.